I was saying from one earlier that in graduate school there were two kinds of people. There were handout people and presentation people. I was a handout person. So
Handout.
So long.
Yeah, a handout.
there's a expanded version of this, which is what I'm working from on Notion.
Is it all one page?
Yeah, I think
Oh,
that's enough for everyone. Yeah.
There's example.
So basically 3 parts. And I'll try to spend most time on the 3rd part, which is the fun part, which is like kind of my take on what new things over the last few years, especially the last year, in search information retrieval seem to be like taking off, working well. People are successfully using where the research is. Try to kind of focus on things that might have some sort of link to what we're trying to do. But the first 2 parts will be kind of setting the stage a little bit. So one will be just when people talk about information retrieval, kind of in the literature, so to speak, like how they conceptualize the problem, some of the kind of terms that they'll use and see, and then just like a brief kind of history of like modern information retrieval research, which really kicked off in kind of around 2016 with the release of this big data set called MS Marco. This is a definition of the kind of core search problem, information retrieval problem, from someone named Jimmy Lin at the University of Waterloo. I really like this definition for a couple of reasons. So it says, given an information need expressed as a query queue, the text retrieval task is to return a ranked list of K documents from an arbitrarily large but finite corpus of documents that maximizes a metric of interest. So I like this one because it distinguishes between the information need and the query. So there's like what the kind of in our case what the user like wants when they're typing in the query to elicit, and then there's like what they actually tell us. And the problem is to address the information need, not necessarily the query. I also like it because it's kind of like a tractable. It makes the problem kind of tractable in a way that I think like mostly works, in that we identify there's like some metric. We'll talk about kind of common metrics in a second that we want to do well on, and that's considering like the ranked list as a whole. So it's not just like this kind of bag of results. It's like we have this like we want to turn this ranked list, and that ranked list is the thing that we want to do well on. And like a few more kind of terms that get used. So relevance, maybe kind of obvious, but typically in information retrieval literature, this is like either kind of like a binary or like a ranked thing. So like mostly somewhat are very or somewhat or not relevant, or just like a binary. This is like relevant or not. As opposed to like some kind of like more fine-grained continuous score. And then the term document gets thrown around, and that's like the thing that's getting ranked. So it might be like a document, like a search result, or it might be like in the context of like if we're like doing QA and we want to find like which paragraph, then the document is actually the paragraph in this context.
Or an entity.
Or an entity, yeah. So it's just like whatever is showing up from this list of results, it can be returned. These are our quote-unquote documents.
Wait, why is relevance binary?
Relevance is binary or graded because we typically are interested in like human judgments of relevance, and they it's like kind of a false precision to ask for something that's kind of more fine-grained than that. And then a qrel is like an actual unit of data that we use in evaluation. That is the human judgment of relevance. So you typically see these like qrel files that look like this. There's like some query, some document, and then the human judgment. Higher is better. So this is like maybe this was phrased as like not relevant, somewhat relevant, very relevant. You see like 0, 1, 2. And then, so if you have a bunch of qrels, you then use those to evaluate you can use those to evaluate your performance on a retrieval problem for some corpus. And so those qrels are often what we call they're sparse in the sense that they're probably lots of actually relevant documents that just the humans never saw when they're evaluating them. And so it's really nice if you have dense qrels, ones that where every possible relevant document was marked as relevant. But that's typically rare. Maybe we'll have that if we're doing QA, where somebody's read through the entire. What was that? Okay. Chewing. Oh, gosh. Okay. Maybe we'll have that if we're doing QA, where somebody's read through and they've marked. We've marked comprehensively these are all the paragraphs or sentences that we think are relevant. Another way that you might get dense qrels is if you're using GPT-4 or something to generate them, and you just go through all the documents and try to for all the queries and try to make some judgment. So dense qrels are really nice because they lead to more accurate evaluations. They're also extremely expensive. So you typically have sparse ones.
In this rendering of the qrels, is the given the query, okay, so we don't care about, this is not indicating any sort of re-ranked search. It's just
so these are just these aren't paying attention to rank. Humans in this case aren't, in most information retrieval data sets look like this. So they don't give you this is the ideal rank. They just give you, here's a query, here's a document. Is it relevant or not? Or how relevant is it?
Okay.
So the most kind of common important metrics / my favorite. My favorite is this one called NDCG. I'll talk about in a second. Another common one that you want to look at is just the precision at K. So K is just some cutoff. I want to look at 5 or 10 search results, and it's of those results. How many of them are relevant? What percentage of them were marked as relevant in qrels? So of your top 10 search results, how many of them were? How many of them did the humans mark as relevant? The NDCG I like a lot. I think it's a very it has a very good quality that you typically want in search results, which is you actually care a whole lot about the ranking and not just getting the results in your results. You really want those super relevant documents to be 1 or 2. And it's worth a lot less if it's 5 or 6, because people just don't read down that far. And they'll look at the first few and kind of make their judgments. And if those are bad, then you kind of lose. And NDCG tries to capture that. So the way that, if you want to think about how the NDCG works, is you can kind of build up from right to left. So the first is this concept of cumulative gain. Cumulative gain is just in your search results, how many you add up all the qrel values. So if you have 8 search results and number 1 was a very relevant, that's worth 2 points. And number 3 was a somewhat relevant, that's worth 1 point. And the rest were not relevant, then your cumulative gain for your set of 8 search results is 3. Discounted cumulative gain weights the number of points by a factor from the rank. And so it's 1 over the logarithm of the rank. And so that means that your first result is ranked by 1. Your second result is ranked by it's kind of down-weighted. It's only worth kind of 0.6 as getting the first result. 1 over log 3. 1 over the logarithm plus 1. Then your third result is only worth half of what your first result is worth. And so this is logarithmically declining weight. So that's the discounted cumulative gain that plays out effect.
How fast do people tend to use the same base?
Log base 2 typically,
okay.
Yeah. And then the normalized discounted cumulative gain takes into account just how many relevance judgments there are. So it says if you were to kind of theoretically do perfect and get all the relevant ones right up front, what score could you possibly get? Because if there are only 3 in your corpus, your maximum discounted cumulative gain is like 2.1 or something like that. And so the normalized discounted cumulative gain just divides your discounted cumulative gain by the maximum possible, theoretically possible one.
So you need to know how many relevant ones you have.
You need to know how many relevant ones are on the corpus. Yeah. This is where like these dense ones are super helpful because they help make that a lot more of an accurate score.
How much does the literature look at like the it's navigational query subproblem? Like I'm trying to find this specific paper or something.
Yeah, I mentioned that a little bit below related to intent classification, query intent classification. There's just like an item here for us to talk about. There's some kind of recent work on that, but there's like some applications where people like try to use LLMs to do this. Yeah, so it's like kind of one thing that there's a little bit on.
Yeah. It seems like in practice probably a thing that people use search engines for quite a bit. It's almost like a browsing thing. I want to get back to it.
Yeah, navigational queries versus information seeking queries versus in like the broader literature like commerce queries.
What kind?
Like commerce.
Okay.
Yeah. I want to buy something. So that's like the kind of like intro to the problem, how it's typically framed. I'll talk briefly about kind of what happened when Microsoft released this giant data set called MS Marco. So very often in like the kind of, I guess like especially in like the 2010s, late 2010s, they're like a big data set and that like kind of like with the availability plus availability of GPUs led to like a ton of progress on some problem that had been like stuck for a while. So like very famously, this ImageNet data set led to the development of this like first really successful classifier called AlexNet, Jeff Hinton. The MS Marco is kind of that for search. So MS Marco contained 1 million real Bing user queries, and it was filtered to queries that were the form of questions. So like, will I qualify for OSAP if I'm new in Canada? Or in what type of circulation does the oxygenated blood flow between the heart and the cells of the body? And then it included then 3.2 million web pages. And then kind of amazingly, they paid contractors to label passages from these web pages as whether they answered these questions or not, and then write actual answers to these questions. So that then you can sort of slice and dice that data set to create a couple different kinds of challenges. One is like, given a query, like in some web page, in like a corpus of web pages, return like the right web pages. One is like given a query and then given these like passages, these like chunks of web pages, return the right passages. One is then like a re-ranking challenge. So given a query and given web pages that like contain like a bunch of keywords from that query, basically, rank them so that the ones that actually answer the question show up towards the top. Then what's kind of influential about this data set is it's big enough to train models with, to train neural networks with. So it's like and this was kind of the advent of like modern neural retrieval. This is like the embedding model that Elicit uses, was initially trained on MS Marco data set. And so you'll typically see like a lot of models still like have MS Marco data set like somewhere in their heritage.
When did that come out?
The data set was in 2016. And then there are like various kind of improvements and additions to it over the years since then. So okay, so that's kind of the history. So now we can like just talk about cool stuff. So I made a list of like kind of cool stuff that's kind of been taking off in the last year or so. With some eye towards like things that might help us. So there's like one category of things that's like just focusing on that problem of the relationship between the query and the information need. This is called like query understanding. There is one kind of like a whole bunch of papers that are tackling this re-ranking problem in a new way that kind of had been like seen as mostly computationally infeasible before, which is before what you typically did is you had some really, really cheap way to go over your entire corpus and return some long list of relevant documents. This is the retrieval stage. And then in some pipeline, then you'll do like a re-ranking or multiple re-ranking stages like we do in Elicit. And typically those re-ranking stages will then look kind of at the query in one passage at a time and like come up with some score. But that's more expensive than the score you get at the retrieval stage. To then do like kind of more expensive, more refined scoring of all those papers, then you sort them by the scores, and that's like a re-ranking. And then you might have like a yet more expensive model on some smaller number that then is like probably even like more high quality scores. What a lot of people are playing with now in a lot of different ways is at this re-ranking stage, taking an entire list of search results, feeding it to a model that can then see all of them at once and then decide on some re-ranking, instead of just giving a score for each one in isolation.
Because now we have more context window.
Is that because more context window?
Yeah.
Yeah, so that's like one of the, like, it's still like quite expensive, but like one of the ways you can do it is you have like these long context models, so you can just like stick a bunch of like, documents in the thing and be like, please give me a ranking. So I have an example of a prompt, I think, on the back of the handout, where they're doing exactly this. There's like, they just give a list of all these search results and say like, please put these in an order for me. And then there are, you can like chunk up your list of search results, like kind of a windowed fashion, do a bunch of those, and then kind of repeat that whole process multiple times to kind of refine the ranking. That's still like quite expensive, all things considered, and quite slow because you have these very long prompts. And so there's also a lot of research on Listwise re-ranking, where you essentially treat each document as like a token, as a single token, and you kind of you stick like the embedding of that document into that language model, and then this model's kind of specialized. It has this like full cross attention across these like single embedding per document, and then it can provide scores, but based on that full cross attention for all of them. So that was a little bit technical, but like the basic idea is it's a much more efficient way to do list-wise re-ranking. You can do it over 500 or 1,000 documents in like a single relatively cheap pass, but the model can still sort of see all the documents at once and making that judgment.
Wait, can I try and say that back to you?
Yeah.
So what you're trying to do is like rank 100 million documents. You can't possibly put like all the paragraphs of those documents into a context window. You have a language model that's very good at token prediction. It says, given this token, what comes next? And so you kind of use that mechanism to say, like, given one paper, what comes next is like, that's the ranking sequence. And then the way you fit the 100 million documents into the context window of the language model is to like embed it, collapse it, embed its text basically into a number or a token, and then say like, paper number 1 is captured by this token, paper number 7 is captured by this next token, and then the language model can say, okay, after token 1, I expect to see token 7 or token 9 or whatever, or something like that.
Yeah, so the first bit, like that, like one way you do it is you just like stick the text in and then ask it to generate like to write out the sequence.
Yeah, that's
right. The second bit is actually not using like a generative language model. It's using like an encoder language model, like a BERT being like the most famous old school now, version of this thing. where it is it's not generating text. It's just like providing a value for each of its inputs. So like these encoders could be like in the past would be used to like provide like to classify each word or something in a sequence as to like whether it's like what part of speech it is or something. That'd be like a really old school way of using BERT. Well, this would be provide like output kind of a score for each like you can imagine word, except instead of putting in just text, we put in we kind of skip the token to like first layer of the model stage, and in that like first layer of the model, we just put an embedding that represents that we got somewhere else from a different model that's trained alongside this one as the first step in that encoder.
People use that mostly to push speed and efficiency, or to be able to fit even more documents in.
I mean,
both, I guess. Yeah.
They kind of come together. Yeah.
Yeah.
For a lot of real world retrieval problems, you're under like really intense time constraints, and so even like kind of like having one long decent generative model and generating like a couple of tokens is too slow.
Do you know where this is being used now? Is anyone actually using this?
Who's using it out there?
Yeah.
I've seen some like demos of people using it in various places. I don't know places. Yeah, I don't know anywhere.
So, and it would have to be embedded in like a BERT-friendly way, like whatever you use to embed the document.
It would be kind of like something that's been trained kind of special purpose on this Listwise reranking. Which leads to the fourth one of these, which I kind of already hinted at, which is generating training data with GPT-4. That's the other big trend. Everyone's doing this. So you could combine these two things, where you use GPT-4 to generate not just qrels but like ranks for you, and then you can train these Listwise ranking models with objectives that are based on those ranks, and so you get kind of more fine-grained things than you get through traditionally with qrels.
When you do like, particularly for ranking, when you're doing these score generations, this is usually like, here's 10 things, tell me a number or something that says, or reorder them what you think the optimal ranking is, or like have people compared that versus something that's more head-to-head. I'm spacing on this one right now. Chess.
Like pairwise
comparisons, and use that to generate the ranking. Because I feel like I'm semi-skeptical on GPT-4, like not being weird about giving me the items generate the optimal ranking.
The Listwise, yeah. So there are things like very obviously when you use GPT-4 for this, it's like biased by the input order, for example. You can mitigate that to some extent by in two ways. One is like just like doing it repeatedly and having it refine it, and then two is over a large enough data set, just like randomizing the input order. And just having that bias to in some sense kind of wash out. The pairwise is there was some I've seen papers that do like try to get GPT-4 to generate pairwise judgment. I think I've seen that at least once.
I guess like it's when I think about like what's in the data, the like ranking seems less seems a more general less obviously a kind of task that's in the training data, or like ELO using these two things, which one is the better one? Seems like a more straightforward assessment for the model to make.
Pairwise, in order to generate like a lot of data, you need to make a lot of pairwise judgments, and that's probably like the main constraint there.
Yeah.
Kind of dumb question, but these methods that you're describing, how much better are they in terms of performance against just GPT-4?
The Listwise non-GPT-4 method, for example,
or even just like kind of hybrid approaches?
So a lot of these approaches that I kind of talk about here, you just can't, are like computationally infeasible to use GPT-4 on.
Yeah.
Like, kind of no matter how much money you want to spend, unless you want to like wait for years. So they're not really comparing the same things. I think it'd be comparing like other re-ranking approaches to over like relatively small amounts to using GPT-4 for re-ranking. And the answer is like there are lots of people who have claimed to beat GPT-4 with some of these approaches. So there's a paper called Rank Vicuna, I think, that claims to have like both distilled from and beat GPT-4 on these things. I'm like typically skeptical of these sorts of claims. I think maybe at best they're like kind of close.
It's probably faster, I guess, right?
Often they're faster, they're smaller, they're cheaper, significantly cheaper. Yeah.
For pairwise, I wonder, it seems like that, like it's not n squared, like you can effectively use it to sort. So it's like you can synthesize, the list with n log n.
Right.
But yeah.
It's also a relative, if you're thinking about using it for training data, you want to think about how like kind of efficient your training data. You want them to be kind of difficult comparisons, or enough of them to be kind of difficult comparisons to get a good signal. Okay, so time, 20 minutes. So a couple of the like other new trends. One more here. Which is they're like new leaders on the main like MS Marco tasks in the last year, and these typically come from like actually like kind of surprisingly maybe like kind of architectural and training scheme improvements. It's some combination of like much better open source pre-trained LLMs, but you can't really just like use a pre-trained LLM and get like good embeddings for search. It's just that there's nothing kind of internal to the model that really like kind of fits the search task well. The model's really optimized for this.
Do you mean like the query document embedding distance when you say?
Some kind of metric that you use these embeddings, stick them in some kind of metric space. But what does work is kind of like jerry-rigging these like very strong models to where you create this kind of like embedding bottleneck somewhere in the model that the model has to use to do some sort of like further fine-tuning or pre-training task that's closer to the ultimate embedding task. So like one that's at the top of this leaderboard is called this Condenser model because it like condenses through like this single kind of embedding in performing this objective of a contrastive loss, which is a fairly straightforward thing. It's just that embedding needs to get different parts of the same document close to each other. So there are these to that, and then like finally some like improvements in sampling efficiency when you're then fine-tuning these models. In particular, there's this like kind of sparse qrels problem that I mentioned earlier, right? Where you actually have like a lot of relevant documents that just aren't marked as relevant because the human evaluators, the labelers, didn't see all the documents. They couldn't make those judgments. And that historically leads to like a lot of inefficiency when you're trying to train on this qrel data because you just have a lot of false positives. False negatives, I guess. You just have a lot of documents that are relevant, but your data set marks them as not relevant. We could get into the details, but basically some people have like really thought about that problem and like tried to come up with some improvements both to like the loss function and then like how we sample documents to try to like either eliminate those kind of remove some of those false negatives from the data set / not make them be as impactful on the loss when you're fine-tuning the model. So I think like those kind of three combinations of things kind of working together, hard to tell like which ones are most important, have led to like kind of beating the leaderboards in the last year on the main MS Marco tasks.
So to clarify, this Condenser with contrastive loss, that's like the same kind of approach, right? That comes together?
Yeah, the condenser is like you kind of identify like some kind of embedding that's going to be like crucial to the operating of the model that then you're going to then use. And the contrastive loss is like an unsupervised, you just have to have a lot of data, you don't have to have any labels, way to try to train that embedding.
And the idea was like the contrastive loss was different parts of the same document get closer together because you assume if they're in the same document, they're more relevant to each other.
Yeah.
It's not equivalent to doing query document similarity embeddings, right?
It's not the same thing. Yeah, it's like a further kind of pre-training task that transfers really well to the actual like final kind of fine-tuning task that you'll do to get on that embedding task.
Okay.
And contrastive loss is like not like a new invention. It's kind of the combination of these things.
And then it's a fine tuning of a pre-trained model.
Yeah, or kind of maybe you can think of it as like sometimes it's like further pre-training in a way, because you just have a ton of unlabeled data, and then you finally fine tune it on some kind of labeled data.
What about full text search though?
What about full text search? So yeah, we're thinking about doing full text search. How does that work? Generally, as far as I can tell, most people in real life are using either just sparse approaches that are augmented some way, or hybrid approaches. And so sparse, so these terms like sparse and dense, sparse or bag of words approaches treat queries and documents just as kind of what it sounds like, a bag of their words. And you generate some statistics that are like, how often does this word appear in this document? How often does it appear in the corpus? How often does it appear in the query? And then you have some mathematical function that's based on those counts, and you use that to score documents and rank them. So those are sparse approaches. Dense approaches are like the embedding approaches, like we've been talking about, where you have some language model that's generating this embedding. When you do have documents that are typically historically longer than the input, it's changed a bit. It changed longer than the context window model. It's changed a bit now. People typically do these they'll either break that document up, they'll chunk it, they'll try to like intelligently choose which parts to embed using some other model, selection. Now, like they will sometimes try to just do the whole thing with a long context model. So that's kind of this year's like sparse attention, although that's not the only trick. And then finally, I've tried to make this work in various Plywood things. I have trouble. I'm not sure. I haven't found. I'd be really curious to actually talk to Joe Christian at Vespa about this. He knows people who are really doing this. There are these late interaction approaches. Late interaction is where you embed kind of all the different parts of your document, and you store all of those embeddings. But then at query time, you have some function between the query and the actual list of those embeddings instead of each one separately. Those are like late interaction approaches. Colbert is probably like the kind of one that you may have heard of. But honestly, they're fiddly. It'd be really nice to make them work. They kind of theoretically are pretty cool, but they're fiddly. They are supported kind of in principle in Vespa, and most vector search engines don't support anything close to them.
What's the benefit of this?
The benefit of that is that you can kind of get like these embeddings of this whole long document without losing all of the detail. Ideally, that function sort of picks up. It takes that query and then it kind of the parts of the document that are like relevant to it, if they are relevant, like really get to light up, and you get a score for that whole document based on that.
And this is for both of these not really affecting ranking at all, right? To some extent.
Both of these.
Talking about like bag of words, what you've been talking about in the
Yeah.
search session are mostly about
Just what people
for
do.
kind of first phase of the retrieval.
Retrieval, not reranking. Yeah. Then in real life, there are lots of ways people try to enhance this, like make up for some of the weaknesses of the sparse approaches. Namely, in that like it has no sense of like synonyms, right? All the stuff that you get from semantic search, you don't get from these sparse approaches. You have to have these exact keyword matches in order to get some sort of result. And one way, a couple ways that people kind of try to mitigate this. One is document expansion. So when they're indexing the document, they'll have like a model read it and then like identify like a bunch of extra keywords that maybe aren't in that document and add that to the kind of the bottom of the document.
Index time SEO.
Index time SEO, yeah. And then you can also do that on the query side. So when they write the query, you can like add a bunch of words to the user's query. Like use that to try to get extra documents. And then one like relatively new thing that's a kind of evolution of that is this notion of pseudo-relevance feedback. You can actually use this with sparse and dense approaches, but it's kind of maybe more interesting in the sparse case, where you do a search, you get back an initial draft list of documents, and then you do some statistics basically on that draft set of documents to decide what new words should I add to my search, or how should I reweight the words in my initial search to do a subsequent search, and then you actually just show the subsequent search results to the user. And so that's another way where you don't even have to have any kind of semantic embeddings, but you get something that kind of feels like semantic embeddings.
So you do a search, you figure out, as an example, you do a search for aspirin and you get a bunch of stuff and they talk about painkillers and you're like, well, I should probably just search painkillers too.
Yeah, something like that, yeah.
Automated query refinement.
Yeah, or you search for Tylenol, you get the things that mention Tylenol also mention acetaminophen.
Yeah.
And the acetaminophen is like one of these like, it'll like light up in these kinds of algorithms because it's pretty rare across all documents. And when it doesn't, but when it is like a document is about acetaminophen, it'll tend to mention a bunch of times. And so then you'll get acetaminophen results, even though you only had a sparse index. You have no kind of embeddings. You can do the same kind of really analogous thing with dense embeddings. There's no reason it needs to be limited to sparse embeddings, but people, in real life, this is a thing that's really used. We'll use this pseudo-relevance feedback with sparse embeddings.
Is that something? It seems like something you could also use for like essentially updating the index. Like you've now learned something. You don't have to recompute that every time somebody searches for Tylenol. Potentially, like if you're able to
if you
out.
could, if you have the right kind of setup. Document expansion, not just by like adding a bunch of keywords, but by generating like propositions, and then maybe kind of interestingly like embedding those propositions or like putting them in your embeddings. This is like an interesting idea. It's been proposed. I actually haven't seen it. I don't know if it's used or not. And then there's a lot of work on like improvements to these late interaction models. There's lots of very active research on this, which is why I'd really love to see it actually working in like some of our real use case. So enhancing Colbert with a version of pseudo-relevance feedback is one of these. It's Colbert PRF.
What does embedding generated propositions mean?
Like, so you is that when you say proposition, do you mean like something that would be like a query that would discover this document?
So like claim-like things. So if you kind of are optimizing search for question answering, for example.
It's like claim pre-extraction almost.
Kind of like claim, pre-extraction, or like these kind of things have like a nice semantic structure if you're searching for claims, maybe more than the kind of the original document. So you do this kind of two-stage thing at indexing time, where you identify some propositions and then embed those.
You can almost, I don't know, it's interesting thinking of like abstracts. In some ways do some of this, which is that like an abstract is often somewhat a list of propositions of like what this paper claims it is doing. We'd like distill down.
Yeah.
And we would like to have these for things that are on papers sometimes.
Generate those propositions. Yeah. So I think that's everything. I guess I skipped over the the kind of research on like the query understanding subtasks. So this is just like a kind of a list of these like that things you might do to try to get better at the relationship, just the relationship between that information need and the query, or understanding the query. So one is given a query, like have this task of like describing what relevant results would be like, and then use those to improve your retrieval.
Is that use a language model to do that, or have the user do that, or something else?
Yeah, I guess I'm kind of putting in here that like these are traditional query understanding subtasks that people are like currently applying large language models to.
How is that done traditionally?
Get a person to do it?
Through like knowledge graph elaboration, or like identifying, so like non-LLM ways to give like some kind of structure to what the results should be like. Elaboration, that is like expanding on the user's query in a way that should ideally improves the results if you use it. Query augmentation, I kind of mentioned that connection with the sparse results. So using the language model at query time to like add some extra stuff to the query. Intent classification, getting a language model to say like, oh, actually, this isn't an information seeking query. They just want this paper, and then like routing it to like a thing that just gets that paper. Prompting the user for clarification, and then given like a session, like a user writing multiple queries, trying to identify like what their next query would be.
Of stuff here, what are things that you see being like fairly near term, things that like we could potentially do, things that Vespa might do for us, either add prompting or unprompted?
So Listwise reranking as one of our re-ranking stages.
You mean using the fancy stuff? Using some full document cross-attention thing, or just like call language model and say re-rank this list?
TBD, but like maybe the medium thing where you have some full language model that's like distilled from GPT-4 at this listwise re-ranking task, and then using it in a GPT-4 kind of style way, where it's a lot slower than the kind of really specialized thing, but in certain contexts we're okay with that if it can improve quality a lot. So listwise re-ranking, I think, like is just like works really well. People just never shied away from it in the past because it was computationally infeasible. It's becoming a lot less so. I think if we do full text search, some kind of hybrid approach.
I'm really a big fan of hybrid stuff. Just being like, depends on what you're searching for. I feel like often embeddings are like not actually what you want.
Mm-hmm.
Yeah. Maybe PRF applied to the sparse component, especially of pseudo-relevant, of hybrid search.
I feel like particularly in our domain, the hybrid search thing where it's like, oh, you search like some compound. It's like, no, actually I really do only want papers that literally include the name of this compound, pretty much always.
Right. Yeah, and so like a semantic embedding that kind of smears that out is basically useless.
Yeah.
Possibly better embedding model. So there's just like ones there that are like work a lot better on the data sets that we that the embedding model we used was trained on. And so it might make sense to do this.
Yeah, that seems like the easiest. I think maybe I'm wrong, but it seems like the easiest. It seems like the most dropping.
Yeah.
LLM re-ranking seems maybe weird for cost reasons, like speed reasons.
Mm-hmm.
What do you think? Oh, sorry. I feel like the really exciting world is the one in which we can just try like a million different approaches in kind of a live setting with users and just have like automatically running A/B tests, getting feedback, and like, you know, multi-arm bandits type stuff, or like just run like 5 different versions of searches for the same query, something like that. Like what would we need to get to that world?
I think we're not that far if we're testing out different re-ranking approaches. I think for retrieval, there's a version of it that's like cheaper to do. Not like, I see James perhaps one thing back here. Cheaper to do, where there's if we have like we're trying this out. It's limited to like archive, let's say. There's 2.5 million-ish documents as opposed to our full corpus of 15 million. It's big enough to be like very real world, small enough to be kind of practical to like kind of, you know, cheaply try out more things.
And then that's it. And then some way of getting user feedback, and then like that's basically it. And I guess some infrastructure for like running all these variations at scale.
Yeah, some way of getting user feedback is maybe like draw the rest of the owl, but yeah.
Because like if we do have if we decide to build a custom connection to archive or incorporate that as like its own corpus, then we could just run experiments on just that corpus.
If we do
I will say, when you asked this question, like what do I think we're trying, I was kind of focused on like what would actually be implemented. I think the actual thing that I think we will really like to try is just like use GPT-4 to at least generate some evaluation data, and get qrels or get like Listwise ranks from GPT-4, validate that against, you know, our real label data, what we care about, and then use that to like much more cheaply and you know, valuably iterate on some of these approaches. Yes.
I assume that it would be a good idea to use if you've got like a HNSW and then a dense re-ranking. I assume it'd be a better idea to have different embedding schemes for the 2 different stages, but I'm not sure if that's true.
Yeah.
And secondly, if it is true, are there any sort of characteristics for the 2 different schemes that would be?
Yeah, typically we like don't even bother with just like embedding semantic similarity for re-ranking because we have a small enough number of documents at that point. Maybe 1,000. That it's just like worth it to do something that's more expensive than embeddings. But to answer your question, like using the same ones, HNSW is not like perfectly accurate. It doesn't have perfect. That's what's cheap. But like, so you would get a different rank a little bit if you just like, you know. But actually, this isn't true. The way that I put this, you would get like the documents you got back would be like ranked correctly from HNSW.
Yeah.
You just would miss some. Yeah.
If we do build a screening workflow, this seems like a kind of God-given data set for getting user feedback, user qrels, because you're like, here is
This either
1,000 things.
included
Here's
or
the
excluded.
exact list of things that are relevant to my query and parameters, right? Like, it's like an extremely strong, dense signal.
Yeah, I mean, a long time ago, we generated a kind of search evaluation data set from systematic reviews, and the qrels was this paper included in the review or not?
Yeah, I mean, I feel like it's always harder to get user feedback than you think, but you can imagine a world where we like let people rearrange, like drag and drop the results in their search papers and integrate papers from their library. Then it's like of the results they get back, they can re-rank them and they can like add the papers that they already know to be relevant, like search data.
There's a little bit of like recent literature on like implicit feedback signals for search too. Didn't mention here, but we could use. Okay, we're over time, I guess.
Cool. I think you should write a blog post.